Hey everybody, how are you guys? I want to go over the homework from last time and start talking about a little bit more from this chapter. I will go over the homework, then I'll do some review conceptual problems at the end of the chapter, then I'll jump back and probably start 15.2, talking about resonators, which can be a little bit confusing, but let's go over the homework first. So the first problem in the homework was on my guidebook here. On page something, number 8, page 309. And the first one, most of you got 9 that I saw. Most of you got number 9. Number 8, remember this is our equation, is FD equals FSV minus VD over V minus Vs. Again, the D's are the detectors. Well, you can't even see what I'm writing. Let me move over. The D means detector, S means source, F is frequency, V is velocity. So in this problem, we should have known that V is 343. Okay, just put 343 in for that. Pretty straightforward there. And we're solving for, we're still solving for loss of the detector. So we know that the V is going to be 343. And minus, what's VD? It says velocity of the detector is U. You are the detector. You are traveling in auto at 55. Okay? So here's the thing. Remember, the key is the direction, positive or negative direction. It had to be the negative direction, okay? Because if the thing coming toward you is the positive direction, then you going the opposite way is the negative direction. So negative 24.6. And then this is 343 minus positive 24.6 because they're going the same speed, right? Yep, same speed, and that's going the positive direction, so there. And then it says it's sounding its horn at 475. So from there, you just do it out, pretty straightforward, and you get the answer of 548. Number 9, most of you got. Number 9 is pretty straightforward. You know, I don't even need to do it. There you have a submarine moving toward another submarine at 9.2 meters per second. That is, you can make, let's see, that is the first sub, so that first sub is the source, right? So that is Vs, the 9.2 is Vs, and it says the second sub is at rest, so it has a velocity of 0, so Vd is 0, so then you have in water, it tells you the speed of sound in water is 1482, so that's what you put in for V. So the top of the equation is 1482 minus 0, pretty straightforward. The bottom of the equation is 1482 minus negative 9.2, and so minus positive 9.2. Sorry, because we have the source coming back. So minus positive 9.2. So 1482 minus 0, 1482 minus positive 9.2, and then you just have 3.5 megahertz as the answer. As the frequency of the source. So the frequency of the detector is 3.52, slightly higher. Pretty straightforward. And remember, you know if it's right if they're coming closer together. Now number 10. Number 10. I have a sneaking suspicion, and I had a sneaking suspicion before. I have a sneaking suspicion that some of you guys aren't really doing the homework. You're just writing down the problems and submitting them again just to make sure you get credit. I will remind you, some of you messaged me and said, I didn't understand number 10, which I expected. Number 10 was tricky. How to solve, but basically you had to do is solve for Vs, which is very tricky to do. It's pretty tricky to do. Some of you might have been able to do it, but it's tricky. So some of you that I expected not to be able to solve for Vs had it perfectly done correctly, okay? And I was very puzzled by that because so that kind of confirmed my suspicions that some of you are just writing down, just using your book, your answer book that you found online or something like that and writing down the answers. I don't want to see that. I don't care about that. I'm not counting your homework toward your grade. I want to see something submitted, but do your best. I don't need to see the right answers submitted, okay? I want to give you, I'll probably, I don't even think I'm counting homework. I'm still up in the air whether or not I'm counting homework toward your grade. If I count homework toward your grade, it's going to be basically that you did something and put an effort forward. It's not going to be that you got the right answers. So that's the thing. It's not going to do you any good. You have to try them for real. You have to. I'm looking at you, right? All right, I'm not even going to go over number 10 because I won't give you a problem like that on a test, so don't even worry about it. If I give you a problem on a test, I'm going to have you either solving for the frequency of the source, the frequency of the detector. Pretty straightforward. All right, let's move on to some conceptual problems. On page, what page are we on? 400 and, let's go to page 424. Mastering concepts. Let me get a drink of water and then we'll do it. By the way, the answer on that one, number 10, in case you are wondering, the answer was 11.4 meters per second. You had to solve for VS. If you felt comfortable solving for VS, then you could have gotten it perfectly fine. But anyway, page 424, number 31. What are the physical characteristics of sound waves? Physical characteristics of sound waves. So how can you describe them physically? Well, you can describe them by their amplitude, right? That's how far away they go from equilibrium. You can describe them by their wavelength, right? You could describe them by their, I should have given you time to think. You can describe them by their wave speed, and you can describe them by their frequency. Those are physically what physically you could describe them as. Frequency, how often they go per unit time. Their amplitude, how far they go from equilibrium. The wave speed and wavelength. Now you might say something like, well, what about crest and trough and stuff like that? Well, the crest and the trough are the amplitude, how far away they are from equilibrium. How wide they are is the wavelength, stuff like that. 32. These problems like this are problems that I would really want you to take notes on these conceptual problems, because problems like these, thinking problems, are ones that I'm very likely to use. When timing the 100-meter run, officials at the finish line are instructed to start their stopwatches at the sight of smoke from the starter's pistol and not at the sound of the firing. So in other words, when the officials, so basically the people are standing there, the runners are standing there at the starting line, right? They're standing there at the starting line, and there's an official next to them with a gun up in the air, right? And when he pulls the trigger, it makes a boom. All the runners run. Okay, he's standing right next to the runners. Well, there are people way down the track with stopwatches to test the times, and they're watching, and they are instructed. The people with the stopwatches to check the times are watching for the puff of smoke coming out of the gun, and not for the sound of the gun. Okay. And what is the reason for that? The reason for that is, give you a second. Why would they not want to listen to the sound of the gun going off, but instead watch for the smoke coming up? The reason is because the speed of sound is so much slower than the speed of light. The speed of sound is pretty fast, like 700 or something miles per hour. Pretty fast. But even so, even at that speed, if you're far enough away, it will be like boom, boom, which is like a 10th of a second or 20th of a second. And that can, change record times or whatever. But speed of light is basically instantaneous. You can go around the whole equator twice in like the snap of a finger, right? And so that's why they would look for the puff of smoke, so there's not a delay. 33. We're going to do a couple more of these. 33. Name two types of perceptions of sound. So two types of perception of sound, and the physical characteristics of sound waves that were corresponding. So we're not talking about physical characteristics. The physical characteristics were frequency, amplitude, wavelength, and wave speed. Those are physical characteristics. We're talking about how you perceive sound, how you hear sound. Name two of them. Well, two of them that we mentioned in 15.1 are pitch, which is how high or how low a sound is, and loudness, how loud or soft the sound is. So and it says what physical characteristics do those correspond to? Well, pitch, how high or low it is, corresponds to its frequency. The higher frequency you get, the higher note. the lower frequency, you get the lower note. Now, what does loudness correspond to? Which of those physical characteristics? There's three left. There's wave speed, wavelength, and amplitude. Which one means louder? It is amplitude. And so the bigger amplitude a wave has, the louder it is. The lower amplitude it has, the quieter it is. And with frequency, a higher pitched wave would look like, I can draw it for you. Okay, the wave on the top, the wave on the top is a higher frequency because it has more waves bunched together. The wave on the bottom is a lower frequency, has less waves bunched together. So this would be like a higher sound, like la, and this would be a lower sound, like la. Now notice the height of the wave is pretty much the same. So they would both have the same volume. Okay, if I draw a wave over on the left here, I'll erase this. This wave these two waves here are very different volumes. They may be similar pitches, but they're very different volumes. This is really loud. This is really quiet. Okay? You guys kind of get the difference there? 34. Does the Doppler shift occur for only some types of waves or all types of waves? Okay, so the Doppler shift is what we talked about with the Doppler effect, which is basically if something's traveling towards something, does it as it's traveling toward it and sending out waves, those pressure waves, they bunch up as they're coming toward, or they stretch out as they're going away. The answer is all types of waves. Works for every type of wave, that they would bunch up as you're traveling towards something and spread out as you're going away. 35, last one in this part. Don't need to do 35. Skip it. All right, 12 minutes. I'm going to start. Let's start talking about 15.2. Now, it's a little tricky. We're going to talk about the physics of music, okay? In music, there's different things. Basically, remember we talked about in order to make a sound is a pressure wave. In order to create a pressure wave, you need to make something vibrate. Okay, and different things vibrate in different ways. You have in some instruments, you have a surface that vibrates, like a drum. The surface is vibrating there. Some of them have a vibrating string, like a guitar, or even a piano has a vibrating string that the hammer hits the string and makes a sound. Some instruments have a vibrating reed, like a saxophone or a clarinet. Some instruments vibrate the wind itself, like a flute. They have a vibrating, they vibrate the wind inside of them. So there are different things that are vibrating, but in each instrument, they vibrate in some way. Now the thing is, each instrument, in order to make that sound, they actually resonate. Remember we talked about resonate? And so what resonating is, as you're adding breath for a woodwind instrument, or as you're adding plucking or whatever, you're getting some sort of resonation along that string, or that instrument of some kind. Specifically with like flutes and stuff like that, you have different kinds of resonators. All right, so let's review. I don't know if I'm going to cover this whole thing, but let's review what a standing wave is. You guys remember what a standing wave is? If you remember what a standing wave is, we have like a position right here and a position right here, and you have a wave coming up, going down and up and down, and it hits a boundary and then bounces back and bounces back, and boom, and hits this boundary again. If you've lined them up so that they hit the boundaries each time, they're going to create this loop that will kind of keep going. It'll be a standing wave. And here in the middle, you have nodes, right? You have nodes, which is the area of least distance away from the equilibrium. And up here, you have areas of antinodes, right? You guys remember this, standing waves? Well, you want to create a standing wave when you are making music, okay? You want to create a standing wave when you're making music. Now, follow me with that. When you have an open section of a pipe, so you're going to have a pipe, and in order to have a pipe make a musical sound, you're going to have it resonate. And in order to resonate, you're going to be creating a standing wave. You guys understand me? So you want to create resonation, and when it resonates, in order to resonate, you got to create a standing wave. Okay, got me with nodes and antinodes. So whenever you have an open part of a pipe, you're going to have a node. Okay, wherever an open part is, you're going to have a node. Okay, so let's say I have an open pipe, a pipe that's open at both sides. Okay, this is called an open pipe resonator. This, which will be open on one side and closed on the other, is called a closed pipe resonator. An open pipe resonator, as I said, wherever it's open, it would have a node. So I have a node here and a node here. A closed pipe resonator would only have a node here. The other side would have this. So this is a node, and this is a node, and this is a node. Here would have to be an antinode. Okay? All right, so what happens here, if you can picture a wave, picture a standing wave like this. This would be one wavelength, right? Everybody knows a wavelength is where it starts, it goes through the whole cycle, and it ends again, it's about to start. This is one wavelength. What it tells us is that the closed pipe resonator is going to be 1/4 of a wavelength. Okay, 1/4 of a wavelength. An open pipe resonator is going to be 1/2 of a wavelength. Or, in other words, it's going to be multiples of 1/4 or multiples of 1/2 if it's longer. In order to get that, in order to get this to be the case, because what you have to do is, let me show you. Let's go with, what should I do first? Open or closed? I'll just draw it. So what you want to happen is, on this one, what it looks like is it comes here and goes there, okay? And if you were to continue, you'd have the whole wave be here, right? So this is half of a wavelength, right? From here to here, because there's a node to node, and then if you doubled it, it would still work to here, okay? So basically it's half the distance. And when it bounces back, though, off of the air, you get this look, okay? And here your antinode is in the middle here. This is your antinode. So it's 1/2 of a wavelength. The full wavelength would be all the way to here. With a closed pipe resonator, it is 1/4 of that, okay? If I want to actually draw it smaller so you can so I can draw the entire wavelength here. With a closed pipe resonator, okay, I'm going to have the antinode, it's got to be here at the end, because if it was to continue, it would continue this way, like that, and then kind of come back, okay? So a closed pipe resonator is going to have 1/4 of a wavelength, because a closed pipe resonator wants to have a node. Where it's open is a node, where it's closed is an antinode. So you have to have that wave fall on a node and an antinode. This open pipe resonator is a node and a node. Okay, so any way that you can split the wavelength to make that work is going to work. So with this one, let's say you had like a full wavelength. Let's say you had doubled it, made it a full wavelength. Would that work? Yeah, a node all the way back to a node again. So node, node, antinode, node, antinode, node. A full wavelength would work for an open pipe resonator. It would not work for a closed pipe resonator because it needs to start with a node and end with an antinode. So 1/4 would work, 1/2 would not. 3/4 would work, a full one would not. You guys understand what I mean by that? So at a wavelength for an open pipe, you need node and node. At the wavelength for a closed pipe, you need node ending in antinode. All right, that's basically what I wanted to cover for today. I don't want to get too deep into it, but I may be kind of just summarizing the rest of the chapter, and we might be moving on to the next chapter pretty soon, but I'll probably only do maybe 1 or 2 more videos, if that. So most of what I want to cover this chapter is in 15.1. I usually don't do too much of 15. So that's it. If you have any questions, I know that open closed pipe resonator stuff is sometimes a little bit tricky. Oh, did I want to give you any homework? Did I want to give you homework? Let me see. Let me just check really quick to see if I want to give you homework. I might not. I might not. I'm in the wrong chapter. Give me 1 second. I apologize. You know what? Try page 426, number 69. It's a problem kind of like what you did last time. and this time actually try it. It's a Doppler effect problem. Number 69, try that, see what you got, and post it for me. All right, thank you. Bye.